So this week we're looking at antiderivatives and initial values, and this is just like the very first thing you do before you get into integration. So the first statement says explain what an antiderivative is. So generally when we're talking about antiderivatives in this context, you'll use big F of x. Now it doesn't always have to be that, but that's usually what it is. So this represents an antiderivative. And usually you'll see big F of x. You'll see this in theorems when we're talking about like the fundamental theorem of calculus. They'll use big F of x. So if that's the antiderivative, and we have f prime of x, if we take the derivative of an antiderivative, we will get the original function. So these are inverses. So in the same way that multiplication and division are inverses, derivatives and integrals are inverse operations. So this will make more sense as we go through examples. But number 2 says explain why it is necessary to have plus c in an indefinite integral. So what I'm going to do is just give you an example of this. So if we had a function, let's say that we're given a derivative. Or let's just try a function. So if f of x is 2x plus 1. So if I take the derivative of that, I get 2. So if I have this f prime of x is 2, and I'm supposed to take the antiderivative, well, I would know that this would have to be f of x, the original function would have to be 2x, but I know that if there was a constant there, it was, when you take the derivative of a constant, it is 0. So there's some number here. And it can be 0, that's fine, or it could be anything, right? So I just know that there's some constant, even if it is 0. So we have to have a plus c to indicate that there was a constant there. So an antiderivative this represents a family of functions. So it's a family of functions, and if you were to graph these, the family of functions, they would differ in their vertical shift. So knowing c gives us a specific function. And we'll talk about initial values and how to get that c value later on here. So the power rule for integrals. So right now we're just looking at one integration technique, and that is the reverse power rule. So normally when we take the power rule, so if we have, this is what we usually do, we'd say take 1 from the exponent and then divide by n minus 1. So this is the power rule for derivatives, but the power rule for integrals is just the opposite. You're going to add 1 and then divide by n plus 1. So whatever the power is, you add 1 and then divide by n plus 1. So this is the only, well, this and some trig antiderivatives, these are the only ones you'll be working with today. So for number 4, write the 6 basic trig integrals. So I'm going to write these as integrals first, and then we'll talk about the antiderivative. So if we have the integral of cosine x dx, so what we're looking at, this is called an integral. The dx indicates what variable we're integrating with respect to, and this little s shape, it's not really an s, it's like a stylized s. So it comes from the Greek symbol sigma, which is a sum. It's telling us to sum a set of terms, which we'll talk about later. But the integral of this, what would you take the derivative of to get cosine? Well, you take the derivative of sine. And we have to have this plus c. So that plus c is a really big deal, particularly if you're taking the AP test. There's always a point for having the c. So if you take the derivative of sine, you should get the integral. So if you go the other way, it's going to be the other way. So let's look at the second one. So the antiderivative of negative sine x dx is going to be cosine. So we're just going backwards from the original function. Next, if we have secant squared, well, what would you take the derivative of to get secant squared? It's just tangent. So these are the derivatives that you were supposed to know off the top of your head. Okay, so we'll write the other 6 here. If we have the antiderivative of negative cosecant squared x dx, you would take the derivative of cotangent x to get that. Next, we have secant tangent. And we would take the derivative of secant x to get secant tangent. And the last one, if we have negative cosecant x cotangent x, we would take the derivative of cosecant x to get negative cosecant x cotangent x. And again, all of these can be derived, but really the 6 trig derivatives and integrals should be memorized. So number 5, how would you use an initial condition when taking an integral to find the correct value of c? Generally, these are given to you in this format. So you'd have some derivative given to you, and then you'll have some value like f of 2 equals 5, for instance. Okay, so what we're going to do is find the antiderivative. So the antiderivative of f prime is just going to be f. And then we, antiderive the function 2, which would just be 2x plus c. And then to determine c, what we do is plug in our 2. So we would have f of 2 equals 2 times 2 plus c, and that equals 5. And then we just take this equation here and solve for c. So this would be 4 plus c equals 5. So c equals 5 minus 4, or 1. So the specific antiderivative that we have would be f of x equals 2x plus 1. So that's how you would take an initial condition to find the correct value of c. And we'll do more examples of that. So let's go to the next example. So this one says, find the antiderivative of the function and check your answer by taking the derivative of the antiderivative. This should be your original function. So if I look at f of x equals 18x squared minus 6x, well, if I antiderive that, and I'll show you the whole process for this now. So that would be big F of x equals 18x to the 2 plus 1 divided by 2 plus 1 minus 6x to the 1 plus 1 divided by 1 plus 1. And we simplify that. So we would get 18x to the third divided by 3 equals, minus 6x squared over 2. And so the simplified antiderivative would be 6x cubed minus 3x squared. And so in that case, I forgot the c, so I have to add the c everywhere. And to verify that answer, we would just take the derivative. So if we take the derivative of the antiderivative, we're going to get our original function. So if I derive what I have right here, so let's say now I have f prime of x. and I should get my function f of x above. So the derivative of this function in blue, or squared off in blue, is 18x squared minus 6x, and then the derivative of c is 0. So since this matches my original function, that tells me I did it correctly. All right, so here's our first integral to work with, 14t to the 9/5 dt. So we're going to find the antiderivative. So we would go 14 t to the 9/5 plus 1 divided by 9/5 plus 1. And this stuff will make you better with fractions because you have to work with them so frequently. So 9/5 plus 1 is 9/5 plus 5 over 5. So you'd get 14t to the 14 over 5 divided by 14 over 5. So if I have 14 divided by the fraction 14 over 5, it's multiplied by 5/14, the numerator would be. So this is just going to be 5t to the 14 over 5 plus c. And really, again, so I made a little, it's not a well, it is a mistake. I need to add a c in here because as soon as I take that antiderivative, I need that c value. So I'd have a plus c right here as well. And so the antiderivative, and this is we don't have an initial value or anything, so this would be the antiderivative. Okay, so the integral of sine 3x plus 5 dx. So we'll work with sine first. So what would you take the derivative of to get sine? Well, we would take the derivative of cosine to get negative sine. So we would have to take the derivative of negative cosine to get sine. And at first, when you do this, it feels like kind of a guess and check. There's a real method to solving these problems that we'll talk about later on. But right now, it is just kind of clunky how we're going to think about it. So when I take the derivative of an antiderivative, I should get my original function back. So if I derive negative cosine of 3x, I should be getting sine of 3x back. So let's try it. Negative cosine 3x, if we take the derivative, that's a chain rule function. So it would be the derivative of the outer function, which is sine of 3x. We'll leave the inside alone. And then we'd take the derivative of 3x and multiply it. So 3 sine 3x is what I would get if I took the derivative of negative cosine of 3x. So it's not quite right. So let's back up, get rid of that, and let's divide this by 3. Okay, so now if I take the derivative, I should get sine of 3x. The derivative of the outer function is sine, leave the inside alone, which is 3x, and then I multiply by 3. And since this 3 is down here, it would cancel and I would get 3x. So, or sine of 3x. So just make sure when you're finding antiderivatives right now that you are making sure that that's, particularly with trig derivatives, that it actually derives to what you need. So the next part's simple though. So what is the antiderivative of 5? That's just 5x. And then plus c. So that would be how to work with a trig function. All right, so this one is like one of the ones we talked about previously. So this is an initial condition problem or initial value problem. And so it says, given the derivative and initial condition below, take the indefinite integral and then apply the initial condition to find the original function. So that's exactly what I showed you just a couple problems back. Just given to you in different notation. So it gives you dy dx is 8x cubed plus 3x squared. And then y of 2 is 0. So that part is the initial condition right here. So let's find the antiderivative of dy dx. And so 8x cubed is going to be, the antiderivative is 8x to the 3 plus 1 divided by 3 plus 1 plus 3 times x to the 2 plus 1 divided by 2 plus 1. And so if we simplify that, we're going to get 2x to the 4th plus x to the 3rd, and have our c. Okay, so this represents y. And let's call it y of x. It's kind of weird, but it's just what it is. And then we're going to plug in y of 2. So y of 2 equals 2 times 2 to the 4th plus 2 times, plus 2 cubed plus c equals 0. So now we simplify. So 32 plus 8 plus c equals 0. So that tells us c is negative 40. So then the original function is y of x equals 2x to the 4th plus x cubed minus 40. So for our last problem, given f double prime of x is x cubed minus 2x, f prime of 1 is 0, f of 1 is 2, find the correct equation for f prime of x and f of x. So like a lot of these questions, this is a AP question, it's confusing sounding, but all it says is, here's the second derivative, find the original function. And since it gives us two initial conditions, we can do this. So let's find the antiderivative of x cubed minus 2x. So the antiderivative of f double prime would be f prime, and that antiderivative would be x to the 4th over 4 minus x squared plus c. And then we want to apply the initial condition. So f prime of 1 is 1/4 minus 1 plus c equals 0. 1/4 minus 1 is negative 3/4. Move it to the other side and you get 3/4. So f prime of x is x to the 4th over 4 minus x squared plus 3/4. Okay, so that's f prime of x. Now we just have to find f of x. So I'm going to shift this over a little bit. Shift it over so I can have more room. And then let's find the antiderivative of f prime, which is f of x. Okay, so this would be x to the 5th divided by 5 times 4, which is 20, minus x cubed over 3 plus 3/4 x plus c. And just like the last time, we apply the initial condition. So f of 1 equals 1/20th minus 1/3 plus 3/4 plus c equals 2. Okay, so let's simplify this all. This would be, if the least common multiple here is 60, so this would be 3 over 60 minus 20 over 60 plus 15, 45 over 60. I had to multiply both by 15, plus c equals 120 over 60. So now I just add these up. So I'm going to get 28 over 60 plus c equals 120 over 60. Subtract to get c equals 92 over 60, which simplifies to 23 over 15. So my function would then be f of x equals x to the 5th over 20 minus x cubed over 3 plus 3/4 x plus 23 over 15. So again, that's just like doing two problems in one.